Welcome to the survey of the elementary principles in classical mechanics. Today we will continue discussing exercises and we will begin with a problem involving two particles joined by a rod. The statement of the problem is as follows. Two points of mass m are joined by a rigid weightless rod of length L, the center of which is constrained to move on a circle of radius a. Express the kinetic energy in generalized coordinates. The constraints placed on particles 1 and 2 and relevant degrees of freedom are given in the following. The distance between them is the fixed length of the rod L. The radius of the circle on which the center of mass moves is A. And for convenience, we want the circle to be in the plane given by z equals 0. As such, the degrees of freedom are the three angles listed here, with omega being the rod's angle of rotation along the circle, and theta and phi are the usual polar and azimuthal angles for one of the particles. Then we make use of equation 131, which stated that the kinetic energy of a system of particles can be decomposed into a term providing the kinetic energy of the center of mass and a term providing the kinetic energy of motion about the center of mass. And for the first one, we just write the coordinates in Cartesian components and then rewrite them in the radius of the circle and angle of rotation. We take the derivatives with respect to time and calculate the squared velocity of the center of mass, and the kinetic energy follows immediately with the expression here. Then for the second term we write the coordinates of one of the mass points in spherical components. We once again take the derivatives with respect to time and obtain the expression here for the squared velocity, and then we simply add the two together. Keep in mind that each particle has mass m, so the total mass is 2 times m, which the factor of 2 cancels the 1 in the denominator, and we end up with the final expression here. And that is all for this problem. Next we will discuss a problem involving a spin-orbit interaction. And the statement is the following. A point particle moves in space under the influence of a force derivable from a generalized potential of the form given here, where r is the radius vector from a fixed point, L is the angular momentum about that point, and sigma is a fixed vector in space. Something like this can be encountered, for example, in nuclear physics. If you want to describe the structure of an atomic nucleus, as a very basic approximation, you can consider a mean field potential interacting with each individual nucleon. In terms of a spherical interaction, you needn't necessarily impose that it is deformed. And then the second term is given by the coupling between each nucleon spin and its orbital angular momentum. In any case, for the illustrative example given here, we are given the following tasks. We are to find the components of the force on the particle in both Cartesian and spherical polar coordinates on the basis of equation 158. We need to show that the components in the two coordinate systems are related to each other as in equation 149, and we are to obtain the equations of motion in spherical polar coordinates. Alright, so to find the force in Cartesian coordinates, we write the potential accordingly and apply equation 158. So here I just wrote u using Cartesian coordinates and the summation convention. So I just wrote out the cross product explicitly, and I also wrote the expression of the angular momentum explicitly. So not a cross product, sorry, this is a dot product. So there's a dot product here between sigma and L, and then I wrote L explicitly as a cross product. Then you just take the derivatives with respect to coordinates and velocities, which are the expressions here. Also being mindful that the index m here is not to be confused with the symbol designating the mass m, but it's easy enough to avoid. And then we, for the derivative with respect to generalized velocities, we also take another derivative with respect to time. And it follows that a Cartesian component of the generalized force has the expression here. And since we are discussing in Cartesian components, it follows immediately that the force is given by the following formula. So it's minus the gradient of the central potential plus 2 times the cross product between the vector sigma and the linear momentum. Now this is an invariant expression, so this is true in all coordinate systems. And it would be then very easy to transform into whatever system we desire, but for the purpose of this problem, I guess what they wanted was for people to practice using spherical coordinates, so we can do the calculations the straightforward way and show that both descriptions are equivalent to each other, both the Cartesian and the spherical one. And for convenience, I've given here the transformation matrix relating the spherical versors to the Cartesian ones, as it is very useful in evaluating expressions such as this in spherical coordinates. And to find the components of the force in spherical polar coordinates, we transform the dot product between sigma and L to the variables r, theta, and phi and apply equation 158. So this is just the vector sigma written originally in Cartesian coordinates. Then I transform the versors to spherical ones and factorize everything, so you end up with the spherical components of this vector, which are the ones given here. And then I wrote the angular momentum initially in Cartesian coordinates. And if you once again apply the transformations, you can find the spherical components of this vector divided by m to have the expressions here, where for the moment I did not write these terms explicitly in spherical coordinates. To do that, we write the x, y, and z coordinates in terms of the spherical ones. We take the derivatives with respect to time, and if we then bring these expressions in the formulas here, we obtain the following dot products between the angular momentum and the various spherical versors. So the dot product with the radial one is 0, and the dot product with the angular versors has the expressions listed here. And as such, we can then calculate the dot product between sigma and L, and we obtain that the generalized potential in spherical coordinates has the expression written here. Now we apply equations 158 and 149 for each of these spherical polar coordinates. So we first apply the definition of the generalized force in terms of the generalized potential, and then the equivalent definition in terms of the Cartesian force. So for example, for the radial component, this is the simplest one. It's just minus the derivative written here. And the result is the one following here. And to use the second definition, we first need the derivative of the radius vector with respect to the radial coordinate, which is the one here, and then we can simply write the r component of q by this expression, and we know who fx, fy, and fz are from the previous result, and it follows that we obtain the exact same expression for the radial component of the generalized force. In an identical fashion, we can work for the theta component of the generalized force. First, we use the definition in terms of the generalized potential, and we get the result here. And then we can take the derivative of the radius vector with respect to the theta coordinate to get this result. We take the dot product with the Cartesian components of the force, and what follows is what should be the same expression for the theta component of Q. And lastly, we do the same for the phi coordinate. Once again, the definition in terms of the partial derivatives of u, which gives this result. And then we can take the derivative of r with respect to phi to obtain the expression here. We take its dot product with the force written in Cartesian coordinates, and we finally get the same result for the phi component of Q. And to write the equations of motion in spherical coordinates, we begin from the general expression here. The kinetic energy is calculated easily, with the result being the one here. And then if we just apply the partial derivatives for each coordinate, we get the expressions listed below, where we know what quantities stand for each of the three components of the generalized force. So it's a very straightforward and simple problem. It just involves a lot of calculations. It can probably be written in more compact terms if you want, by instead of writing the derivatives explicitly, perhaps using a symbolic notation for derivatives of angular momentum or linear momentum components. But in any case, it doesn't really matter. And lastly, we are going to discuss a problem involving forces in Weber's electrodynamics. The statement is as follows. A particle moves in a plane under the influence of a force acting towards a center of force whose magnitude is given by the expression here. So in magnitude, it looks a bit like a kind of a Coulomb force, but it also has these terms, which involve velocities and accelerations in the radial component, and the square of the speed of light in vacuum. And yeah, r is the distance of the particle to the center of force. We are to find the generalized potential that will result in such a force, and from that the Lagrangian for the motion in the plane. This problem is solved by guesswork. So we know the definition of the force to be the one here, and we can simply try a generalized potential of the form here. So it has a Coulomb component. 1 over r will result in the Coulomb force, and for the second term we can try something like this. And if you calculate the derivatives here for this quantity, put everything together and add them up, you obtain exactly the expression of the force that was stated in the problem. And then you simply write the x and y coordinates in terms of spherical components. You calculate the derivatives with respect to time for these quantities. You find v squared, and the Lagrangian then follows immediately by the expression here. And that is all for now. Thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.